So our goal today is going to be to use derivatives for functions of several variables in an effort to try to find where those functions of several variables reach maximum values and reach minimum values. Especially when you talk about calculus to people in application context. So if you're using calculus in the sciences, if you're using calculus in the social sciences and business and stuff like that, this process of optimization is one of the big selling points for why calculus is a valuable set of skills to have. For example, if I'm developing a new product and I'm bringing it to market, but I have to decide like how much, what price should I charge wholesalers for my product, and maybe what marketing strategy should I use? How should I? That can be a multivariate question. And if I'm trying to get the most profit out of my marketing plan, then that profit is going to be a function of perhaps several different variables. And so if we're trying to figure out how to maximize that profit, we might need to figure out how to optimize it with respect to a wide variety of different variables at the same time. And so we want to develop those tools for optimizing a function of several variables. And so that for us, that's going to be kind of a three-step process. The first thing we're going to look at is how do we do the local process of optimization? How do we go on a search for local minimum and local maximum values of a function of several variables? So that is going to be a process of, just like it is in single variable calculus, finding critical points. These are going to be the possible candidate places where we can find local minimum and local maximum points, and then classifying those critical points. Is it a local maximum? Is it a local minimum? Or is it neither? And so that's going to be the sort of the local viewpoint. But then in practice, especially in applications when we're doing optimization, usually we also have a certain domain on which we need to do that optimization. Like maybe we can't just pick any price that we might want to pick. It's going to have to be like a non-negative price. We can't charge like -$6, right? We don't want to pay people to take our product. And so there might be limitations. There's a domain on which we want to do our optimization. So that's going to be the next step, is how do we do an optimization problem on a closed region, a closed domain. And then finally, sometimes we have more specific constraints that actually reduce the dimension, if you like, of the domain that's available to us. Maybe we can't do an optimization problem on an entire open subset of the XY plane for my domain. Maybe I have to live on a certain level curve or something like that. Maybe for example, if I'm trying to decide how much of my budget to allocate towards labor and how much of my budget to allocate towards physical expenses or something like that, then I don't get to freely choose those two things because they have to add up together to give me my total budget. And so I have a constraint that might look something like x plus y equals 1,500 or something like that. And so that defines not even a sort of a region within the XY plane, but actually just a single curve within the XY plane on which we have to do our optimization. And so that process of constrained optimization is sort of the third step. I think that's probably the one that we're not going to quite arrive at until perhaps tomorrow. And so for today, we want to set as our goal to, first of all, ask the question about critical points. What should a critical point for a multivariable function be? What kind of properties do we expect it to have? And then, and this is probably the most intricate part of today, how do we classify what kinds of critical points exist for multivariable functions? And how do we tell the different kinds of critical points apart from one another? So that will be our goal for today.